So a small little lecture here on truth tables. Now truth tables are not examinable in this module, but I still like to teach them. I think you're going to see them at a later date, and to me they help understand better what union, intersection and not actually are. So the bit says hard to follow and difficult for you to reproduce the proof. So these are pictures, these aren't proofs. The bit I scribbled out, where's it gone? If you were to look at it, it's kind of difficult to follow that. A way of keeping track of the argument and not using as much notation is to use what are called truth tables. It's probably best to introduce truth tables by examples. Okay, so what you do here is you've got two sets, and there's if you have two sets, there's four possibilities for an element. It can be in A and in B. It can be in A and not in B. It can be not in A and in B, and it can be in not A and not B. So basically what this is kind of saying is, it's kind of, if I write down a Venn diagram, there are four different there's four regions of the Venn diagram. I'll number them according to the rows. So the first row is in A and B. That's row 1. Then in A and not in B, because remember we said ones will say yes and B's will say no, but here we haven't got a specific thing, we're just talking about an element that is in A and not in B. So this is row 2. Next is not in A but in B, that's row 3, and then the last one is in neither. So this is why you need four rows. So the first row says, now, yeah, I'll just say in A and in B, I'll just put brackets around these, implies in A or B in the union. That's what the first row really says. If you're in A and you're in B, you're in A or B. Now this is actually in both, but the union does include both. Okay, the next one I'll write, the second row, and similar to third, says in A and not in B implies that you're in A or B. And the last one says not in A. So this is just saying what these ones and zeros actually mean. The last row is 0, 0, 0. Oh yeah, so probably what I should mention here is, so if it's in A or B, you put a 1 underneath. So there's a 1 for in A and in B. There is a, so like looking at here, look, the union is all the elements that are in either A or B. So 1, 2, 3, those three regions are in A or B. So the first 3 rows should have 1s, and the last row corresponding to not in A or not in B, well, it's in, well, be careful there. It's not in A anyway, and it's not in B either. So it's not in the union, so it has a 0. And so I'm going to write that down here. Not in A and not in B implies not in A or B, and so a 0 goes there. So these truth tables are useful to prove some set identities. Okay, so the first one. So first of all, we'll set up the 4 scenarios here. 1, 1, 1, 0, 0, 1, 0, 0. Okay. Now this is one of De Morgan's laws. This is De Morgan, where you see the not, the word is kind of distributing over the sets, and the union flipped to an intersection. It's exactly the same if you swap that from an intersection, that would be a union. So this is De Morgan. Yeah, so okay, let's go. So if you're in A and in B, are you in A or B? Yes, because it's a non-exclusive OR. If you're in A and not in B, are you in A or B? Yes. If you're not in A but you're in B, are you in A or B? Yes. If you're not in A and you're not in B, are you in A or B? No. Okay. Now the not, of course, is just going to be a toggle. So toggle is a word you're going to hear. It's when you either go from a 0 to a 1 or a 1 to a 0. So if you're in A or B, you're not in not A or B. That'll be a 0. Toggle from 1 to 0. If you're in A or B, you will not be in not A or B. 0. If you're in A or B, you will not be in not A or B. And if you're not in A or B, you are in not A or B. So that toggles from a 0 to a 1. So this is the truth table for not A or B. Now what we can show is that if you have equal truth tables, then they're the same set. Is that obvious? Well, let's see. Okay, now let's do not A. So looking at row 1, so this is not in A. Sorry, this is in A, so it's not in A. This one is in A, so it's not in not A. This is a 0, so yes in not A. This is a 0, so yes in not A. Toggle 0, 1, 0, 1, 1, 0, 1, 0. Similar story, just toggling the B's. So the 1 goes to a 0, the 0 goes to a 1, the 1 goes to a 0, and the 0 goes to a 1. And then the intersection. So this is, if you're in the intersection, you are in not A and in not B. Is this in not A and in not B? No, it's in neither. Is this in not A and in not B? No, because it's not in not A. So that's a 0. Is it in not A and in not B? No, because this is a 0. Is it in not A and in not B? Yes, so it's a 1. And we can see that they have the same truth table. So basically they're the same set. It might be hard for me to explain beyond this. I suppose if you have two sets, any two sets, there are only 4 possibilities for an element. And this is showing that no matter what, so the 4 possibilities are in A and not B, A and B, B and not A, or and not A and not B. So there's only 4 possibilities, and this is saying that in any of those 4 possibilities, if a set is in this, it's also in this, and if it's in this, it's also in this. So if they're the same truth table, they're the same set, and it doesn't actually matter what the sets A and B are. So this is like a proof of what's called De Morgan's law. All right. The empty set has no elements, so its membership column consists entirely of zeros. So use truth tables to prove that A or the empty set is A. So you can either be in A or not in A. That's the only possibility here. Now there'll never be a 1 here because you never have something that's in the empty set. So the union, in this scenario, is it in A or the empty set? Excuse me. Yes, because it's in A, so that's a 1. And here, is it in A or the empty set? No, it's in neither, so it's a 0. And we can see that these two sets, excuse me, have the same truth table, so they're the same set. Okay. An ambient set contains all the elements of interest, and so its membership column consists entirely of 1s. Whatever you're thinking about, it's going to be in the ambient set. So let's prove that the intersection of any set with the universal set is the ambient set. We can probably draw that in terms of a picture. It's kind of obvious. So let's draw A intersection U. So here's A. So yeah, in terms of intersection, it's kind of like it's a trivial intersection, you could call it. Just A, I mean, everything that, but this, okay, let's slow down. Everything that's in A and in the universal set. It's not this, because this is not in A. Yeah, it's this, which is exactly the same as A. Let's do it here. So in the first row, you have something that is in A and in the universal set. So is it in intersection? Yes, 1. And the second scenario that's out here, it's not in A, so it can't be in A and U, so that's a 0. So an identity with 3 variables sets the Venn diagram. I think we might have drawn, we have one on the previous page, I think, on page 18. Yeah, just you have to be careful how you draw it. I actually didn't know, but you can draw one 4. It gets a little bit difficult, but you can do it. And all we're going to show here is that you're going to need 4 rows. Now this picture is a bit small, but hopefully we can manage it. And let's go here, 1, 2, A, B, C. Now okay, let's talk about the different regions, and that's how we'll see the rows. So region 1, region 2, region 3, region 4, 5, 6, 7, 8. And if we think in terms of the binary strings we saw earlier, so region 1, I'll do them in order. It's in A, not B, not C. So we got this relationship here with the binary strings, funnily enough. I can't explain it in terms of subsets. We'll just keep writing these binary strings. So this is going to be like in terms of like you read 1 1. For if you've got 3 sets, it'll be like say 1 0 0. Right, let's keep going. So region 2 it's in A, it's in B, but it's not in C. Region 3, it's in B, it's not in A, and it's not in C. Region 4, it's not in A. I think I've made a mistake here. Yeah, because I want to keep the order up, so it should be A, B, C. So this one is wrong. Is this in A? No. Is it in B? Yes. Is it in C? No. This one is in A? No. B? Yes. C? Yes. 5. Is it in A? Yes. B? Yes. C? Yes. 6. Is it in A? Yes. Is it in B? No. Is it in C? Yes. 7th one. Is it in A? No. Is it in B? No. Is it in C? Yes. And then finally 8. Is it in A? No. B? No. C? No. So these will be the 8 rows of the truth table if you've got 3 sets. So here we go. So let's complete the truth table for this. So I'll just take those. Well, the order doesn't matter. So let's do. Actually, we may as well count up. So how do you make sure you write them all up? Well, it's just a side thing here, but you can do 0 0 0 corresponds to the number 0. 0 0 1 corresponds to the number 1. 0 1 0 corresponding to the number 2. So basically what I'm getting at, these are 1s, these are 2s, these are 4s. Like 1s, 10s, 10 squareds. 1s, 10s, hundreds, thousands. 1s, 2s, 4s, 8s. That's binary. And you can just count up from 0 to 7. So that's not necessarily that easy. It's just one way of doing it. I think you'll learn different ways in your computer modules, maybe even like this. But anyway, let's do it like this. 0, 1, 2, 3, because it's 2 plus 1. What do I get? 0, 1, 2, 3, 4, 5, 6, 7. 4 plus 2 plus 1. Let's just count them. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's them. Right, let's do our little truth table. So A or B, so it'll be, now you say it's all the elements that are in A or B. It just has to be in A or B. So if it's in A, it's automatically 1. If it's in B, it's automatically 1. And if it's in both of them, it's also 1. Because it's a non-exclusive OR. So this is not this is in neither, so that's a 0. This is in neither, so that's a 0. This is in B, so it's in A or B. This is in B, so it's in A or B. This is in A, so it's in A or B. This is in A, so it's in A or B. And this is in A, and this is in A. Okay. And now intersect with C. So these are, you have to be in this and in this. So you're going to have to need, like if you've got a 0 0, it's not going to work. 1 0 is not. So this is, it's not in C. And this one, it's not in the other one. So the only way it can work is if you have 2 1s. So this doesn't work because it's not in C. No, it does not. Yeah, this one, yeah, it works. So if you're, this is in B and C, you're in A or B and C. Okay, this one, is it in the intersection? So the intersection, you need 2 1s because it has to be in this one and this one. That's, you have a 1 and a 1. 1 and a 1, no. 1 and a 1, yes. 1 and a 1, no. 1 and a 1, yes. And what you should be able to see if you go back to the Venn diagram is it'll be in 3 different regions. I think if I was to count them, it's probably 1, 2, 3. Okay. Let's see another question. Produce 2 copies of a Venn diagram for this. In the first, carefully shade this. In the second, carefully shade that. Okay, so what we're going to do, we'll do the Venn diagrams a little bit later on. But so suppose you were asked to do this Venn diagram for this. This would be a little bit tricky. It's not the end of the world, but it's a little bit tricky. The easiest way is probably do a truth table. Now C is probably easier, because what we can do is we can draw it and then the knot is outside, so it's okay. So we'll do again, we'll count from 0 to 7 here. 0, 1, 2, 3, 4, 5, 6, 7. Okay, we'll go a bit faster. So we're trying to build up this thing. So first we'll do not A, then we'll do not A or B, and then we'll do this intersecting with this. Okay, so not A is just toggling A. So 4 zeros, 4 ones becomes 4 ones and 4 zeros. Now the union is, it just one of them has to be a 1, and we're looking between this and this. So I got a 1 here, so that's a 1. I got a 1 here, so that's a 1. 2 ones, that's good. 2 ones, that's good. Now here I've got 2 zeros, so is it in not A or B? No. This also gives me 2 zeros, no good. This one, it's in B. This one, it's in B. And now I need to intersect that with C. So to intersect it with C, it has to be in this and in this. So I need a pair of ones. Is there a pair of ones here? No. Pair of ones here? Yes. Pair of ones here? No. Pair of ones here? Yes. Pair of ones here? No. Pair of ones here? No. Pair of ones here? No. Pair of ones here? Yes. And so we've got 3 regions that we're going to do for part B. This one, and finally this one. Okay, so I think we're going to do part B over the next page. Now I'm going to come back to this. Maybe I'll just write them up the top of the page. So we're going to have, with respect to ABC, 0, 0, 1, 0, 1, 1, and 1, 1, 1. This corresponds to not A or B intersection C. Okay, so we'll draw the Venn diagram. A, B, can make that a bit bigger, C. Right, let's write down the name of the set. Not A or B intersection C. Actually, if you don't see what I'm writing there, you could have this problem. So this is why the notation is so important. Okay, so the first one is not A, not B, just C. So that would be here. Because it's not in A, it's not in B, but it's in C. The next one is not in A, okay, but it's in B and C. That would be there. And the last one is in A, B, or C, so that's in there. So there are the 3 things to shade. I think that's a very tricky question, like to, what I say by a tricky question, to actually do that question without a truth table. You could do it, but it'd be very messy. Now, of course, the other thing you could do is produce a series of Venn diagrams, but with, oh crap. Look, we know this bit isn't there. Sorry. Not that bit. But it'd be a little bit tricky. This is probably actually just as quick, well, especially the way I had the truth table already set up. The other one is easier, to be honest. It's just A or B not, so it'll be outside A or B. So no problem there. A, B, C, and let's form A or B. And kind of handy, we just want not that, so outside that, no bother. No real need for any truth tables or anything like it. Now you shouldn't really be thinking, so, oh, is this an exam question I could be asked? It could, but really it's just building up your understanding of things, and really what I want to see is you doing exercises and that building up your understanding. Okay, if you can build up your understanding enough, you know, the exam questions is not going to be too, basically it'll be a question of understanding, not learning questions. Okay, now the next section is going to be one of the harder ones, but we'll just focus on these laws at the moment. So I'll just explain these very briefly. What are they saying? So this is, if you take the things that are not in not A, that's exactly A. We've seen this one, the things that are in A and in the universal set, well, that's just A. Everything that's in A or the universal set, well, everything is in the universal set. So that's why these two are equal. A or, now this one is interesting, A or not A. So everything is either in A or not in A. Everything is either in A or not A. So, and everything is the universal set. What are all the things that are in A or in A? Well, that's just going to be A. This is just saying that the things that are in A or B is the same as the things that are in B or A. This one is De Morgan's law. Now we're going to explain this again a little bit later on, kind of get an understanding going. But this is saying if you're not A or B, so if you're not A or B, you're not A and you're not B, which is what this other bit is saying. This thing is, I don't necessarily understand this. If I was to prove this, I'd probably have to do a little truth table, but it's something like this. A and B is a small set, and so if you take everything that's in this small set or in A, you end up just with A. This is just saying if you look at A and B and then intersect C, it's the same as doing B intersect C first and then intersect A. This is like a multiplying out. Look, it's like A by B. Nearly like A plus B, to be honest. The union is a bit more like plus, and the and is a bit more like multiply. And then A by C, as such. Again, you'd have to use a truth table to convince yourself of this. Then this other one. Everything that's in A or the empty set. Now, there's nothing in the empty set, so you just get A. A and the empty set. So that's all the things that are in A and in the empty set, but there's nothing in the empty set. So there's nothing in this intersection. This is all the things that are in A and not A. Like, that's not, there's nothing that is A in A and not in A. So that'll be like the day is raining and not raining. That's not possible. A intersection A is A. Yeah, this is fine. This is the other De Morgan's law. So if you're not A and B, you're either not A or not B. We've mentioned this one. This one's a bit weird. So it's like a big set and you're intersecting with a small set, you end up with A. Here, again, this is just, it doesn't matter the order you do your unioning. And this one, we've got another distribution. So what we're going to be doing is we're going to be using these set laws. Essentially, we're going to do some algebra, some logic with these to simplify some things. But we'll see that in the next section.